Dark matter is one of the strangest substances in the universe. Despite making up 24% of the observable universe, it's still mostly a mystery. But with the use of gamma-ray telescopes, we can peek behind the curtain. But how? Let's start from the beginning. Although dark matter is invisible to conventional telescopes, its existence is inferred from its gravitational effects on visible matter. For example, when plotting the velocities of stars in a galaxy against their radial distance from the galactic center, there is an unexpected difference between theoretical plots generated from gravity theory and those plotted from observational data. The masses at further distances orbit much faster than expected from theory. This is what led scientists to the idea of dark matter, a substance that only interacts with gravity and not with light. Another form of evidence for dark matter is how it interacts with the cosmic microwave background. Both ordinary and dark matter interact with the CMB, but in different ways. In the early universe, ordinary matter was strongly ionized and interacted with the CMB radiation through Thomson scattering. Dark matter, however, does not interact with radiation, but it still interacts with the CMB on large scales through its gravitational potential. These different interaction methods mean that the perturbations they cause evolve differently over time and leave different observable imprints on the CMB. So, how can we use gamma rays to detect dark matter? Well, let's look into the theoretical candidates for dark matter particles. Among them, three primary contenders stand out. First, we have weakly interacting massive particles, or WIMPs. WIMPs are some of the most studied dark matter candidates, arising naturally in extensions of the standard model like supersymmetry. Their masses typically range from a few gigaelectronvolts to several teraelectronvolts, which makes them excellent targets for indirect detection. WIMPs interact through gravity and the weak nuclear force, which allows them to self-annihilate and produce secondary particles, including gamma-ray photons. When it comes to WIMPs, one of the most promising processes is annihilation. In many models, WIMPs are their own antiparticles, so when two WIMPs collide, they annihilate, producing high-energy particles like quarks, leptons, and gauge bosons. These particles then decay or radiate, generating gamma rays through several pathways. Neutral pions produced in these interactions can decay into 2 gamma photons, contributing to a broad spectrum. Charged particles may emit photons directly through what's called final state radiation, which alters the gamma ray spectrum, and sometimes WIMPs can annihilate directly into 2 photons, creating a sharp, distinct spectral line, a potential smoking gun signature. The energy of this line corresponds to the mass of the WIMP, making it a powerful tool for detection. Then there are axions and axion-like particles, or ALPs, originally proposed to solve the strong CP problem in quantum chromodynamics. Axions are extremely light particles that can interact with photons in strong magnetic fields. This unique property allows axions to convert into gamma rays in extreme environments, like the magnetospheres of neutron stars or the turbulent regions of galaxy clusters. The third candidate is sterile neutrinos. These hypothetical right-handed neutrinos do not interact via the weak force like ordinary neutrinos. However, they can decay radiatively into a standard model neutrino and a photon, creating potentially observable X-ray or gamma-ray signatures. Discovering these would offer deep insights into neutrino physics and into physics beyond the standard model. By studying the gamma-ray spectrum, scientists can attempt to distinguish between signals from dark matter and those from natural astrophysical sources. Sharp, narrow features in the spectrum, called line emissions, are a hallmark of direct annihilation or decay. To illustrate the differences between sharp, narrow line emissions and broader, diffuse continuum emissions in the gamma-ray spectra, consider the following examples. The spectrum shown here displays distinct sharp peaks corresponding to specific gamma-ray energies emitted from the galactic center. Each peak represents a gamma-ray line emission resulting from direct annihilation or decay processes. This spectrum illustrates a continuous distribution of gamma-ray energies without distinct peaks, characteristic of continuum emissions resulting from secondary particle decays and interactions. Searching for the sharp, narrow line emissions is a primary objective for gamma-ray telescopes like the Fermi LAT, the HESS, the High Energy Stereoscopic System, and the upcoming Cherenkov Telescope Array. However, differentiating these kinds of signals from natural sources like pulsars or supernovae proves to be challenging. To improve these searches, theorists are constantly refining their models. They're considering things like how dark matter clumps together through gravity, particle interactions, and the way cosmic rays propagate through space. They're also embracing multi-messenger astronomy, combining gamma-ray data with neutrinos, gravitational waves, and X-rays to build a clearer picture. To detect gamma-ray signals from dark matter, scientists utilize a combination of space-based and ground-based observatories, each offering unique capabilities. Firstly, we have the Fermi Large Area Telescope, launched in 2008. Fermi LAT scans the entire sky every 3 hours, detecting gamma rays across a broad energy range, from 20 MeV to over 300 GeV. Its wide field of view and continuous monitoring have been instrumental in identifying gamma-ray sources and searching for dark matter signatures, such as the unexplained gamma-ray excess in the galactic center. Our second instrument is the Dark Matter Particle Explorer, also known as Wukong. DAMPI is a Chinese satellite launched in 2015 designed to detect high-energy gamma rays, electrons, and cosmic rays. It boasts exceptional energy resolution, particularly in the range of a few GeV to about 10 TeV, making it adept at identifying sharp spectral features that could indicate dark matter interactions. Our final space-based observatory we will be covering is the International Gamma-Ray Astrophysics Laboratory, also known as Integral. Integral has been operated by the European Space Agency since 2002. Integral focuses on detecting lower energy gamma rays, specifically in the keV to MeV range. One of its notable detections was a strong 511 kV gamma ray line emitted from the galactic center, which has been investigated for potential links to dark matter decay, though alternative astrophysical explanations exist. Then we have the ground-based observatories. While Earth's atmosphere absorbs gamma rays, ground-based telescopes employ the imaging Cherenkov technique to detect the brief flashes of Cherenkov radiation produced when gamma rays interact with our atmosphere. The first ground-based telescope we will cover is the HESS, or the High Energy Stereoscopic System. HESS is located in Namibia and comprises 5 telescopes. It is sensitive to very high energy gamma rays, ranging from 30 GeV to tens of TeV. It has conducted extensive surveys of the galactic center and nearby dwarf galaxies, searching for gamma ray emissions indicative of dark matter annihilation. Our second ground-based telescope is the Major Atmospheric Gamma Imaging Cherenkov. As this is a bit of a mouthful, we know it as MAGIC. These telescopes are situated on La Palma in the Canary Islands. The MAGIC system consists of 2 telescopes, both with 17-meter mirrors. They are particularly sensitive to gamma rays starting from energies as low as 25 GeV up to 30 TeV. MAGIC has dedicated significant observation time to studying the galactic center and other previously mentioned dark matter-rich regions. Finally, we have the Very Energetic Radiation Imaging Telescope Array System, or VERITAS. Located in Arizona, United States, VERITAS is an array of 4 12-meter telescopes that detect gamma rays in the 85 GeV to 30 TeV energy range. It has been actively involved in indirect dark matter searches by observing dwarf spheroidal galaxies, which are considered prime targets due to their high dark matter content and low background emissions. While all these telescopes work efficiently in the ways they were intended to, scientists are always looking toward the future at how other possible observations could be made. In the not-so-distant future, the Cherenkov Telescope Array, or CTA, represents the next generation in ground-based gamma-ray astronomy. Once operational, CTA will consist of over 100 telescopes of varying sizes, distributed between sites in the northern and southern hemispheres. This extensive array will significantly enhance sensitivity and energy coverage, ranging from 20 GeV to 300 TeV, providing unprecedented opportunities to detect faint gamma-ray signals potentially linked to dark matter. So far, despite many searches with these telescopes, dark matter has not yet been directly detected. But gamma-ray observations have provided some of the most intriguing clues in the hunt. Let's start with one of the most talked about discoveries, the galactic center gamma-ray excess. In the early 2010s, data from the Fermi-LAT revealed a surprising result. There was an unexpected excess of gamma rays coming from the center of our Milky Way galaxy, with energies peaking at around a few GeV. This excess looked consistent with theoretical predictions for WIMP annihilation, possibly indicating dark matter particles colliding and producing gamma rays. Naturally, this generated a lot of excitement. However, other astrophysical sources, especially unresolved populations of millisecond pulsars, could also explain the signal. Later analyses, using better statistical techniques, showed that the signal might indeed be clumpy, suggesting discrete sources rather than a smooth dark matter halo. Regardless of this, the Fermi Galactic Center excess remains one of the strongest hints we have of a potential dark matter signal. Next, we turn to dwarf spheroidal galaxies, tiny faint galaxies that orbit the Milky Way. These galaxies are interesting because they're dark matter dominated and have very few background gamma ray sources. They're considered some of the cleanest places to look for dark matter annihilation signals. Fermi-LAT has also been used to observe dozens of these galaxies. So far, no significant excess has been found, but that in itself is important. These non-detections allow us to place strong upper limits on the dark matter annihilation cross-section. In other words, if dark matter is annihilating into gamma rays, it's not doing so very often, or it's happening below our current detection threshold. Another intriguing result came in 2012, when some researchers analyzing Fermi-LAT data claimed to find a narrow gamma ray line at around 130 giga-electron-volts near the galactic center. A line signal is particularly exciting because it would be a clear smoking gun signature of dark matter annihilating directly into two photons, something very hard to mimic with ordinary astrophysical sources. However, further studies revealed issues. The signal's significance dropped with more data, and instrumental systemantics couldn't be ruled out. Most researchers now believe it was likely a statistical fluctuation or an artifact of the detector. There have also been other efforts, including observations of galaxy clusters and the extragalactic gamma-ray background. These studies help place constraints on dark matter scenarios, especially for decaying dark matter models where gamma rays are emitted over long timescales. And of course, ongoing work continues with instruments like the HESS, MAGIC, and VERITAS, which focus on higher energy gamma rays. So, while there have been no definitive detections, gamma-ray astronomy has significantly tightened the net around dark matter. We've ruled out many models and narrowed the parameter space for what dark matter can be. And some signals, like the galactic center excess, continue to generate active research. As our instruments and techniques improve, future observations may finally tip the balance from possibility to discovery. Now let's take a look into the challenges and alternative explanations of dark matter signals previously mentioned. This is going to require a deep dive into the mathematics behind dark matter. One of the key tools in the search for dark matter is an equation that describes the expected gamma ray flux from dark matter annihilation. By applying this equation, scientists can predict what a dark matter signal might look like, and then compare that prediction with actual data. The process begins by selecting a target region that's rich in dark matter, such as the galactic center. From there, researchers calculate something called the J factor, which depends on how dark matter is distributed in that region. They also use particle physics models to estimate how much gamma ray emission should be produced. Once these predictions are made, they're compared with observations from gamma ray telescopes like Fermi-Lat or HESS. If there's an excess of gamma rays beyond what's expected from known astrophysical sources, it could be a sign of dark matter. Otherwise, the data helps place constraints on dark matter properties. Let's break down this equation. On the left-hand side, we have the observable, the gamma ray flux, what the astronomers actually measure. The right-hand side contains two key terms. First is the particle physics term, which tells us how dark matter annihilates and what kind of gamma ray spectrum it produces. This term here is the velocity averaged annihilation cross-section, which reflects how often dark matter particles annihilate. This is the mass of the dark matter particle. This is the branching ratio, which gives the likelihood that annihilation will produce a specific set of particles. And this differential describes how many gamma ray photons are produced per annihilation per unit of energy for a given final state. Then we have the astrophysics term, the J factor. This captures the spatial distribution of dark matter. It involves integrating the square of dark matter density, ρ, along the line of sight. In other words, it adds up the contribution from all points between us and the target region. The J factor essentially tells us how much dark matter is in view and how it's arranged in space. Now, there's an important reason why this equation matters so much. Measurements of the cosmic microwave background, the afterglow of the Big Bang, tell us how much dark matter exists in the universe. These measurements imply a specific value for the annihilation cross-section, about 3 × 10 to the power of -26 cubic centimeters per second. And here's the interesting part. This value is what you'd expect if dark matter interacts via the weak force, just like particles in the standard model. This coincidence is known as the WIMP miracle. It suggests that weakly interacting massive particles are a compelling candidate for dark matter, and if WIMPs are real, they should occasionally annihilate and produce gamma rays in regions where dark matter is dense. That's why this equation is so powerful. If we know, or assume, how dark matter is distributed, we can use the equation to learn about particle properties like mass and annihilation rate. Or if we know something about particle physics, we can turn it around and use gamma ray observations to learn about the structure and density of dark matter in the universe. When searching for dark matter signals, one of the biggest challenges is separating those signals from background noise created by ordinary astrophysical sources. Objects like pulsars, supernova remnants, and cosmic rays all contribute to a background that can mimic or mask the signals we're looking for. Let's take pulsars, for example. These are rapidly rotating, highly magnetized neutron stars that emit various particles, including electrons and positrons. Thanks to their intense magnetic fields and fast spin, these particles can be accelerated to incredibly high energies. In recent years, the contribution of pulsars to the cosmic ray spectrum, especially to the number of positrons, has gained a lot of attention. One key piece of evidence comes from the Pamela satellite, which observed an unexpected excess of positrons in the cosmic ray spectrum between about 10 and 100 GeV. At first, this raised excitement. It could be a hint of dark matter annihilation, but pulsars offer a more conventional explanation. Nearby pulsars like Geminga and this, along with the collective output of mature pulsars in the Milky Way, could easily account for the observed positron excess. These pulsars produce high-energy positrons that travel through space and contribute to the positron signal that we observe on Earth. What's more, these contributions could produce a small but measurable dipole anisotropy, a directional difference in the cosmic ray electron spectrum. This anisotropy could help distinguish whether the positrons are coming from pulsars or dark matter. Telescopes like Fermi may be able to detect this subtle signal, offering a way to resolve the source of the excess. But pulsars aren't the only competition. There's also uncertainty in how dark matter is distributed throughout the galaxy. This distribution plays a critical role in determining how much gamma-ray flux we should expect from dark matter annihilation. Different models predict different results. Two common ones are the NFW profile and the INASTO profile. Each describes dark matter density differently, especially near the center of the galaxy. Unfortunately, our observational tools like galaxy rotation curves and gravitational lensing aren't always precise enough to fully constrain these models. And while we know that galaxies like the Milky Way are surrounded by dark matter halos, we still don't fully understand the structure and density of said halos. These uncertainties make it hard to predict how much gamma-ray flux we should see and where we should see it. This leads to a major challenge. Even if we detect something, we can't be completely sure that it came from dark matter and not from some other source. This also impacts calculations of the J factor, which determines the contribution of dark matter along the line of sight. If the density profile is uncertain, so is the J factor, and so is our prediction of any dark matter signal. Given all these complications, some researchers have looked beyond dark matter altogether. Instead of adding a new kind of invisible matter to explain galaxy behavior, modified gravity theories suggest tweaking the laws of gravity themselves. One prominent example is modified Newtonian dynamics, introduced by Mordechai Milgram in 1983. Mond proposes that gravity behaves differently in regions with very low acceleration, such as the outer edges of galaxies, where standard gravity fails to explain the observed rotational speeds. These theories can successfully explain some galactic scale observations, and for some researchers they offer a compelling alternative to dark matter. However, modified gravity theories struggle to explain large-scale phenomena, like the structure of the cosmic microwave background or the behavior of galaxy clusters, where dark matter models tend to perform better. Still, Mond and related ideas remain under investigation and continue to challenge our understanding of the universe. Looking ahead, one of the most promising upcoming missions in gamma-ray astronomy is Gamma 400, the gamma-ray astronomical multifunctional modular apparatus, as well as the previously mentioned Cherenkov telescope array. Planned for launch after 2026, this Russian-based space telescope is designed to take the next step beyond current instruments like Fermi-LAT with significantly improved energy and angular resolution. A major goal of Gamma 400 is the indirect detection of dark matter. The mission targets two leading dark matter candidates, WIMPs and ALPs, but it's also open to exploring other possibilities. Some of the exciting prospects include detecting narrow gamma-ray lines in the galactic center, as well as searching for ALPs from nearby supernovae or bright gamma-ray pulsars. There's also potential to investigate other sources like globular clusters and active galactic nuclei. In conclusion, the search for dark matter through gamma-ray observations represents one of the most exciting frontiers in astrophysics. From the earliest hints of dark matter in galaxy rotation curves and gravitational lensing, there still remains many unknowns surrounding it. However, we've since developed sophisticated theoretical models such as WIMPs, axions, and sterile neutrinos that give us a roadmap of what to look for. Using cutting-edge instruments both in space and on the ground like Fermi-LAT and HESS, scientists are scanning the skies for gamma-ray signatures that could point to the presence of these elusive particles. From sharp line emissions to broader continuum signals, the gamma-ray sky holds clues that with enough precision and patience could reveal the nature of dark matter. Of course, the path forward is far from straightforward. One of the biggest challenges is disentangling potential dark matter signals from the vast background of natural gamma-ray sources, things like pulsars, supernova remnants, and active galactic nuclei. On top of that, our theoretical models must be continually refined, especially as new data helps to constrain what is and isn't plausible. Still, with new observatories like the Cherenkov telescope array on the horizon, offering even greater sensitivity and resolution, this may help us distinguish dark matter signals from background noise with more confidence than ever before, resulting in us being closer than ever to solving this cosmic mystery. Whether it's through a subtle spectral line or a surprising excess in the data, the universe may yet offer us a glimpse into its hidden matter.